So these are different missions that use different types of propulsion. Cassini really just has monopropellant rockets, actually. So it got shot out by its launch vehicle, by its rocket out to Saturn, and then it uses conventional rockets to get into orbit of Saturn and to make changes. And the reason it does that is because it's near Saturn, it's near the gravity well, so it needs a little bit more power. It can't really use an ion engine. But something like Dawn, which is just going to asteroids, which have a lot less gravity, it can use really efficient ion engines because it doesn't need that extra power. So it can use less fuel and be really efficient. So there's a trade-off. So this is why you might want a more powerful but less efficient engine here, because you're dealing with a larger gravity well. And in the case of New Horizon, it doesn't have any engine at all. It just was launched by its launch vehicle, and it's just going to fly by. So it's not able to make any changes to its velocity at all. It's just going to keep flying. Yep.
Just to any asteroids or comets nearby which might hit it.
Yeah, they do. They would well, so asteroids and comets are big, asteroids are small. They wouldn't be able to see most of, we track less than 1% of all asteroids. So if there's something out there near Pluto, that there could be definitely something we don't know about. The thing is though, space is pretty big and asteroids are really small, and I think there's about 80 million asteroids in our solar system, but that's not actually a lot compared to how big the solar system is. So your chance of hitting an asteroid, have you guys seen Empire Strikes Back? You know when they're flying through the asteroids and stuff? It's not like that at all, unfortunately. If you were in the asteroid belt, I don't even think you would know it. There's an asteroid here, and then like 100 kilometers away, there's another asteroid. You know, the asteroid belt is not dense like that. There may be asteroids belts that are, but not in our solar system. Yeah, exactly. Well, that's probably right. In fact, there are, the rings of Saturn are kind of like an asteroid belt of really small asteroids. So that's exactly what happened. And what happened, people think that maybe the rings of Saturn were a moon that broke up because it got too close to Saturn, and so it was broken up by the pull of Saturn's gravity. You're right, if there's a lot of asteroids there, but that's why maybe in the early solar system before the planets formed, maybe there were a lot of asteroids. Maybe the solar system had a lot more, but many of them formed into planets, right? So you could picture a big asteroid belt like that, maybe in a new solar. Yeah, Cassini is flowing through Saturn's rings. The rings right now are basically dust. They're like little tiny particles, water droplets, things like that. It's not like chunks of rock. I mean, there are probably some chunks of rock within it, but the biggest pieces are probably like a meter or two, but the majority of it's just like dust and grains of ice and stuff like that. And every spacecraft that we have also orbits the sun in some way. It's not necessarily a circular orbit, but it could be an elliptical orbit. All right, so just an example of how you get to Mars, you have to change into Mars's orbit. And this is what Galileo did to get to Jupiter. Just to give an example, we launched it from Earth, and then it flew by Venus to do a gravity assist to pick up energy from Venus. And then it flew by Earth again to pick up more energy from Earth. And then flying by Earth shot it out all the way to Jupiter. So you don't necessarily launch things directly. Sometimes you can do what's called a gravity assist, which means you fly by a planet really, really close and use its gravity to slingshot yourself on the other side. In an atmosphere, you need to figure out a way to land with resistance. But sometimes that resistance is really helpful because you can actually use that to slow down. And that's how we actually get back to Earth, and it's how we land things on Mars. Sometimes you use a heat shield. That's Curiosity, actually. This is the payload. Payload is why you launch the satellite in the first place. This is a radio communication satellite, so its payload is all based on antennas. So it senses signals coming from Earth. Now these antennas are in completely different bands, completely different frequencies from the antennas it uses for communication. It actually has two different antennas it uses for communication, two different frequency bands. And the higher the frequency, the more data you can get down, but the more narrow the spectrum has to be. So the more sensitive your antennas are and the more power it takes and that sort of thing. But here's an example of a camera payload. You have a star tracker, so it's able to tell what the camera's pointing at. Star tracker is basically a separate camera that looks at the star positions, and based on where they are, it can tell where it's pointing at because it has a catalog in its computer of the whole sky, of what it should look like. And so it's a pattern matching. So it says, oh, there's a star there, there's a star there, there's a star there. It's a particular pattern, and it tries to match that to its database of what the entire sky looks like, and so it knows where it's pointing. And it has an antenna on there, X-band antenna, and payload housing. This is an example of Juno, the Juno mission, and this was to go to Jupiter. And it has magnetometer, so it's to measure magnetic fields. It measures gravity gradients around Jupiter to map out the gravitational field. So this measures charged particles coming from Jupiter. Jupiter's a bit like a mini sun. It gives off more heat than it actually gets from the sun. If Jupiter's bigger, it would be a sun. And there are a lot of solar systems that actually have multiple stars. Spectrograph, so spectrometer, it measures ultraviolet emissions, so it takes in light and matches that light to different signatures from chemicals, so you can tell the chemical composition of something by looking at the light coming from it. Camera, microwave radiometer, so it measures microwaves. But basically you have all kinds of scientific instruments that sense different things, either about the light or the magnetic field or the charged particles, or it uses radar or LiDAR or something like that, spectrometer. There's all kinds of different science instruments you can have. So this is a really long magnetometer boom from Cassini, so it senses magnetic fields. It uses low gain antenna and the high gain antenna to communicate with Earth. Plasma wave subsystem antenna, so that measures plasma waves. Remote sensing palette, I think that's a whole suite of instruments there. Radio isotope thermal generator, so that's its power source. That's Huygens probe. This fields and particle palette will have all kinds of sensors to measure magnetic fields and charged particles and things like that. And it also has radar, so it can do radar maps of moons of Saturn and Saturn itself.
Is there any probe or like spacecraft that has
I don't think so. Because really, any engine assembly requires control systems, and it requires a fuel tank, and it requires a lot of extra hardware and weight. So to have both at the same time would be a waste of weight and other resources. You're going to want to choose whichever one's better for your mission rather than having two sets of hardware, because it's really expensive and in terms of weight to have two sets. Okay, so this is Phoenix lander. It has LiDAR. I guess that's in here. So it shoots up a LiDAR beam, which is kind of like a laser beam. It's a different kind of light. And it measures the clouds. And so it bounces back from the clouds, so it can tell all kinds of things like the composition and the height and the density of clouds on Mars. It went to the Mars polar ice cap regions and sampled the soil. It has a robotic arm to dig soil, and it has an oven to heat it up and have the gases come off, and then it can sense the gases using a spectrometer. Thermal evolved gas analyzer, that's the one that would be able to sense the gases and what's in there. It has a camera, descent imager, and a stereoscopic imager, so two different imagers there. So basically, it electrochemistry and conductivity analyzer. So its purpose was threefold: to measure the weather on Mars. It's like a weather station. That was actually a Canadian instrument, the LiDAR. To take pictures and to sample the soil. And so all its instruments are built around that purpose. This is Mars Science Lab. It has a camera, actually two different cameras. It may have others as well. Sieves and scoop. It's basically able to pick up and sample dirt. It basically has a chemical lab. It has a laser for penetrating rock and measuring the density of rock, and for imaging it as well. So it basically is able to drill with a laser and measure composition of different kinds of chemicals in the rocks, take pictures, and sample the soil are the main things you would want to do, and sample the chemistry of the soil. Something like Viking lander, its purpose was to analyze the soil and determine if there was life on Mars. Because when we sent this was the first lander we sent to Mars in 1976, they had no idea what Mars was really like on the surface. And so it scooped up some soil and ran a series of 4 science experiments on the soil. And they actually came back inconclusive. We don't really know. A few of them came back negative, and a few of them came back inconclusive. Because what happened was they took in soil samples, and when they put it in an oven, they got chemical conversions. So they got different chemicals coming out of it than went in. And so it means there was some kind of chemical process. And that could have been an indication of life. So all you do is if you put like oxygen in, and if it changes to carbon dioxide, for example, you know that there's something breathing there. If it's a microorganism or something, that's kind of the way you test for life, is you put in one chemical and see if you get out a different chemical, because all life is chemical reactions. It's converting something to something else across an energy gradient. So we convert food and oxygen into energy and work and various other things. So they weren't sure, based on the results of the experiment, whether there was life or not. Most scientists thought probably not, but the lead scientist thought maybe there was something going on. But anyway, I think that it probably was a chemical reaction, because there's other things that can do that instead. And so that's what we're trying to find out with Curiosity, one of the things. Actually, it has a seismometer too, to measure like tremors on Mars and earthquakes. So back to the full view, as a recap, this is basically everything in every other spacecraft, except it doesn't have an engine, this particular one, but it does have attitude control. So you have power, you have a way to get to orbit or get launched off Earth. You have computers that control everything. You have communications with Earth, so you need to be able to tell it what to do and receive its data. You need to be able to tell where it is and control where it is. You need to keep it warm with thermal control, or cool sometimes. And you need a payload. So you need some reason to send it, which is what it is actually there for.